So today we're going to discuss neural networks and deep learning. And this is what, when you hear in the news, an artificial intelligence has managed to do this or that, it's mostly because of deep learning is involved somewhere. What I propose is to discuss a bit how it works for smaller neural networks, describe a bit the problems that they can solve with some examples, and then run a case. So we will cover neural networks, deep learning. There are two versions of deep learning architecture which are quite popular, so convolutional neural networks and recurrent ones. And as a hands-on exercise, today we're going to use this data set that is used to check if we could, from the images, recognize which number is in there. And the application is that we can read handwritten numbers for the zipped code in the letters and help a post office to automatically route the mail to the appropriate region of a city depending on the zip code. So for neural networks, I would like to start with a simple example. So let's say that we have one neuron and it looks a bit like this. So stay with me, it's a bit tricky. So I put the pointer, laser pointer. These are the inputs. So for instance, in the example that we had last time, where we predicted the price of a house in Airbnb in Frankfurt, this for instance could be the number of ratings you have, or the average rating, or the neighborhood. So these are features that you give, so information that you provide. These weights are coefficients, so you multiply this input by a number, and this is what you get here. So this notation is basically you multiply the weights by the inputs and you add them all together. And this is the first part of the neuron, if you like. And the second part computes an activation. The activation is a function of Z, and Z is what was computed there. So the function is a sigmoid function, and this is how a sigmoid function looks like. So this is the formula for it, and this has the shape. So for every set that you put here, you get the corresponding activation. And this will be a neural network with exactly one neuron. We can have more neurons, and the spirit is quite similar now. Instead of having one, you have several, and then you combine all together. How you train the neurons? I don't know how many of you were here for the linear regression case, but at that time we discussed that we can use an optimization technique that is called gradient descent, and basically we want to minimize the error. So the error can be given by this formula. I mean, it's not important to understand, but basically what we're doing is we're comparing the real value with our prediction. We square that and we add all together and take the average. So we just want to minimize our error, and the error has this shape. So what we're doing is that we have a learning algorithm, and the learning algorithm, what it does is it changes the weights so that we go down in this optimization process to minimize the error. So we want to arrive at this point. So for learning the last layer, what we do is the weights are the weights as they were minus the gradient with respect to this weight, multiplied by a learning rate that is alpha. No? And it's minus because we want to move in the opposite of the gradient. So the gradient at the end is the slope of the cost function. So we want to move down. That's why we have a minus. This is quite similar to what we discussed, that we want to solve linear regression with an optimization function instead of the least square method. The tricky part will be how to optimize this weight here. And for this we use the chain rule. I don't know how much you remember for calculus, but I don't want to go too much into details. What I want to say is that if you know the derivatives at this point, you also know the derivative of the sigmoid function, and knowing these two, you can go back and propagate the error so that you optimize the weight. Okay. So what is deep about the deep learning? This will be like a shallow network, and this is a deep network. In the sense, this one is not very deep, so it has only 2 layers, but you can make it as deeper as your slide allows you. So I only have like space for 2. So what's good about deep learning? I took this slide from somebody else. Here's the reference at the bottom. What I like is that other techniques, if you have small amount of data, possibly other machine learning techniques work better. But if you have a lot of data, you can really benefit from deep learning because it scales much better with the amount of data. Normal machine learning or older techniques, they have like a saturation point that when you have more data, it doesn't improve. But deep learning keep improving as you throw more data to it. That's the beauty of it. The other thing that makes it interesting is that it's a representation learning. So it can learn representations, like discovering hierarchies that are present in the data by itself. In the case of recognizing faces or image recognition, usually first layers detect this kind of shape. So you have like edges or textures. In the case of faces, you can see like a part of faces, like eyes or nose and so. And layers, which are a bit more higher level, they recognize full faces. The other advantage of deep learning is that they usually need less parameters. So if you want to have 6 neurons here, you will have a total of 40 parameters. Here, having 6, you have 30. And usually what happens is that the deep representation has more capabilities. So it can learn more things because untangle this hierarchy with less parameters. So deep learning is the way to go if you go for neural networks. And neural networks have been around for many, many years. So why is that we didn't take deep learning for longer, for so long, no? That we didn't take it? Neural networks experienced like they were fashionable for a while, but then there was some issues, and then support vector machines were the way to go. Till recently, that deep learning are overtaking, in almost every other technology. And the reason is some of them I think you can imagine. So we have more data. The more data you have, the better. So data is good. And to process all this data, we need more processing power. So now deep learning is trained with the GPUs, so graphical processing unit. So we take all the progress done by gamers that they happen to develop the same technology that we need. But even if we had this amount of data and the same power we have now, 10 years ago, it would not be possible. There was another technical factor that prevent us to use deep learning, and this was the vanishing gradient problem. So let me discuss in a minute what it is. If you remember what we discussed before, that we optimize using an optimization technique that minimizes the cost, and we have this learning using derivatives, and with the chain rule, we go layer by layer and use the derivative to go back. This has an issue if you have many layers. And there are 2 problems. If you realize this signal, the sigmoid function saturates at this point, so to the left, and saturate to the right. Okay. So this is the derivative. the derivative also saturates, meaning that it's very close to 0 in these points. So when you propagate one layer back and another back and another back, you have many chances that at any point one of them will be in this region. So the gradient is lost, therefore the signal to correct the error is gone. And one way to solve this was to have a better initialization. Before 2010, so it's very recent, people believed that the best way to initialize was a Gaussian distribution, average in 0, standard deviation 1. Somehow it felt right. No, it's beautiful, perfect Gaussian. But this causes that when you have, depending how your input looks like, you either go in this direction or this other one. So instead of having one initialization method for every neuron in the network, this other initialization was devised. I mean, I don't go into the formula, but the message is that depending on the input and the output, you can have a different standard deviation for every neuron that depends on how many inputs and how many output has. And this allows you to be on this region, which is more linear. Still, this is doesn't solve it. So we have another issue, is that if we have many layers, so let's say that you want to have 10 layers, and if you look at how the gradient function looks like, notice that the scale is a bit different. No? Here it goes between 0 and 1, and here it goes from 0 to 0.25. So in the best case, you get to keep a quarter of a signal. But usually you're not that lucky. You're somewhere here or there. So if you have 10 layers, and each of one you lose like, you keep only 10% of a signal, you can imagine how quickly it disappears. So it's very difficult to have deep networks that you can learn. And it turned out that it's quite easy to solve this problem. But let me show you how it was. So we were using this sigmoid function. And the reason why we're using it is that neuroscientists told us that this is how biological neurons work. So if neuroscientists say so, and we want to be as inspired by nature as we can, this is the way to go. But this inspiration sometimes doesn't work, and in the same sense that birds are our inspiration for planes. Our planes, they don't flap their wings. They found a different way to do it. No? So we have, for instance, this other activation function, which is quite simple. So if it is less than 0, it's 0. You get as activation. And if it is bigger than 0, you get the identity. So this has the advantage that on this side, the gradient will be 1, so no gradient is lost. The disadvantage is that everything here is 0, so there is no way to minimize, to keep minimizing the error when you're in this region. Anyhow, just using this function allowed people to use very deep neural networks, and is sort of the de facto standard activation function. This is what most people use. And it doesn't really matter that it's not derivable at this point, that you have this totally lost at this point, because you have this non-linearity that you need and allows you not to lose the gradient. There has been some proposal on how to improve this. So the leaky ReLU, so leaky rectified linear unit, that is not set to 0. So this is better, but it still is has a non-linearity, so it's not derivative friendly. So the exponential linear unit has this shape that is so nice that you can take derivatives, and it works. It's also kind of another standard now. It was most people use. So that's simple. It's only like a mental thing that we were forcing ourselves to use something similar to inspired by the biological neurons. For generalization, you remember that what we wanted with the previous model that we discussed, like decision trees or linear regression and so, we want our model to behave well in the future. And in this case, it's quite easy to see because we have only one variable. But when you have, as is the case with other machine learning techniques, many variables, you need to have a way to quantify even when you are not able to see. So what we proposed at that time was to split the data in two. So we have our training set that we use to build the model and our testing set to evaluate the model. And checking the error here there in the training and testing, we can understand if the model is not able to learn or is able to learn but is not generalizing well. So this still is true for deep learning, it's just the same. What we add is a new set that we call validation, or maybe some other people call it development data set. And this is to select which model and which hyperparameters, because then this requires some experimentation. In the case you can experiment with 7 layers or 10 layers or 20. And how do you know which one is best? So, well, the one that is best is the one that generalizes better. But if you use the same data to experiment and to check, what happens is that you're kind of cheating and you're fitting your experimentation to the data you have to validate. So we keep the test data really to understand how it feels, how it performs in reality, and we use the validation to play which parameters or to understand which model works best. In the typical classical machine learning where we have few amount of data, this is the typical split. You can use 60% for training, 20 and 20 for validation and test. But in the area of big data, since we have much more data, we just need to have enough data to quantify how good our solution is. So usually you just keep like 1%, 2%, whatever is enough for you to quantify how good it is. For regularization, remember that we want to make our models simpler, as simple as possible. When we discuss linear regression, we had this other incarnation, if you like. So we have lasso, ridge, elastic net, and what we were doing is we added to the cost function a penalty that will also minimize the amount of weight. I don't go into details because we discussed it the other time. What I want to say is that here is the same. You can use the same thing. And I want to show you another regularization that is specific to deep learning. It's called dropout, and it works much better than any other one than L2L2. So it's quite recent. It was invented in 2012. And what we're doing is that for every training iteration, we just drop some neurons randomly with a certain probability. In reality, what we're doing is that we set the output to 0, but I mean, it's like dropping it. So you can have this effect. Looks like it was totally disconnected. And this is proven that allows the network to generalize much better. And the reason for this is that the neurons cannot co-adapt. So this, for instance, this neuron cannot rely that it will complement the result of this one in the next layer, because any one of those can disappear. So they need to be useful by themselves, no? They cannot be useful in combination to other. And also is that if you have some input that might be correlated somehow, you cannot say, for instance, this neuron, I will take the output of this one because with this one I don't need the other, because this one can disappear anytime. So you need to consider all the inputs. And this allows to generalize much better. So this is a bit for introduction for neural networks and deep learning. And I want to discuss some particular version of deep learning architectures. For instance, convolutional neural networks are mostly used for image processing, And I put some examples. For instance, classification problem. You get a picture, and you need to say what is inside the picture. So this will be our problem that we will solve during the hands-on exercise, that we have numbers, and we need to say which number it is. You can also try to guess where in the image is the object, or if there are many objects, classify all of them, or maybe even do like a cutting of where the object is. No? This is a contest that is fostered a lot of innovation in this direction. So there's a contest that runs every year, and the contest is that you're given any image, and you need to say out of 1,000 possibilities which object is inside the image. If it is a car, if it's a dog, it's a house, or whatever. We reach the point now that deep learning is better than human performance. So if it is a dog, it tells you the race of the dog, which maybe I'm not that good at that. Also some funny applications. So it's myself with the rain princess. If you put that together, this is what you get. You can try by yourself, and there are different styles, and you can upload your own picture. But this is another thing convolutional neural network can do. Another thing it does is face recognition. So these are the people in our team. So you can get to know who is in there. So let me tell you a bit how it works inside, so that it doesn't look too magical. Imagine that we have this number, which corresponds to a handwritten 8. And this, in reality, this is how it looks like. So it's a grayscale that you have numbers from 0 to 255. The colors, in reality, are the opposite. So you have 0 is black, and 255 is white, but I reverse the showing because it's weird, no? To have the black background. So this is how it looks. So it's just a bunch of numbers. It's a matrix of numbers, the images. And this is the problem we're going to solve. Our data looks like this. So this number, or this one, it looks like a 9. We need to predict it's a 9. Imagine that we go to a simpler problem, and we say, this is our picture, and we want to build a neural network that tells us if this number is at 8 or is something different from 8. Something we can do is, it is 28 by 28 pixels, so 784 pixels. We can use every pixel as an input. We can have our network and predict yes or no, so if it is 8 or not. And this is a bit of a brute force, but it works, and we will get good results on this. The thing is that if our data is a bit like that you don't know if it will be in the center or not, it stopped working, because it learned sort of by heart the position of the pixels, but it doesn't recognize the shape. So we need something a bit more powerful. We want to really do image processing. So I'm going to introduce convolution operation. Does anybody knows convolution? Or have you played with good? Have you played with Photoshop or GIMP? Yeah, so it's, if you've played with them, you have these filters that you can put. And let me try to give you an intuition of what it is. This will be our image that is based on numbers. Convolution is that you have a kernel, or depending on terminology, people call it kernel filter, and you will multiply each to every position, and you add all together. So here we have 1, 0, 1, so whatever is the multiplication, you have it, and you get a 4. I don't know if it's clear, the example. So this is an intuition. I want to give you another intuition, so I took a random image, let's say this one, And I put this filter, and this filter will blur the image. And I don't know if you see from there, but it's less sharp because this filter averages the pixels around. Maybe it's more clear this other one. This is a sharpen filter, so you see the, especially here, all the letters are sharper. No? This one is to detect edges. Maybe it's too dark, but the letters from ISA, maybe you still see. So this is an intuition what the filter do, and these filters has been discovered by people that work over the years in image processing, and their task was to design these filters. Now the bad news for these people is that we can have deep learning automatically designing this filter for us, and these are the good news for us, that we don't need to do it. So I go a bit more details a bit later, but I want just in this one to give you a big picture idea, high level. So this would be our input layer. So we have our picture, we can put it there. We have a convolutional part that it has this convolutional operation. Typically what happens is that we have, after the convolution, or after some convolutions, fully connected, so like a normal neural network, and then the output layer tell us what we are interested on. For instance, this picture I took from somebody, from a researcher who was investigating breast cancer detection. So he will put a picture, and you will get if it is malignant or benign. Okay. So let me zoom a bit on the convolutional part. You need to say how big your filter will be. In our filter from the picture from ESOC, what I did was filter of shape 3 by 3. This researcher decided to do 5 by 5, but you can do whatever you like. And basically what happened is that you tell the network, I want to use so many filters of this size. So for instance, 32 filters of 5 by 5. And this is what you have. And the image goes through each of these filters. Usually you start with an image which is has already three filters, in the sense that it has the red channel, the blue channel, and the green channel. So you start from these three, and you apply all these three, and after this process you convert your image to a 32 filter after applying convolution. So you have like 32 new images after applying convolution with these filters. And what happened is that we want to reduce the process, because you need to do the convolution on all these filters after all the layers. So usually is followed by a pooling layer. Pooling layer, I will explain in a minute, but what we're doing with the pooling layer is we're reducing the size of the image. And it's as simple as this. You get an image, and if you decide to have a 2 by 2 max pooling, you split the image so that you have 2 by 2, and you take the maximum. So, not rocket science. It reduces computation, reduces memory usage, reduces the number of parameters. So, if we put all together, is that we have our image, we have 3 channels, red, green, and blue. We apply these filters, and we also apply the max pooling. And what we get is, every time we use max pooling, we have a smaller image, and the image gets processed, and this thing goes thicker, in the sense that since we have more filters, we have more slices of the image for every convolution we do. What is the beauty of convolutional neural networks? Is that the parameters of the convolutional part don't depend on the image size. So what we're learning are the filters. So it could be any size. If the image is big, it will take it longer. But the thing that we need to learn is the filters, which is independent of the size of the image. For instance, this is one of the images that one of these years won the competition of classifying which of these 1,000 objects will be. Let me make a zoom on it. So you get an image, and you have a convolution, and then ReLU. So ReLU was this activation function. Then a max pooling convolution, max pooling convolution, max pooling convolution. You get the idea. So every time what they do is they make it smaller and increase the number of filters. And at the end, you add a fully connected, so a normal neural network, and it tells you it has an output of 1,000 neurons to signal which of the possible 1,000 objects in this contest was. Something you can do is that these networks, they put the weights and the filters available as open source. So something you can do is repurpose this architecture, because all the convolution, it has learned the layers of detecting maybe objects or textures, things which are round, things which are straight, and they're building a hierarchy, and you can reuse this for your purpose. This is called transfer learning, and usually what you do in transfer learning is that you keep the convolutional networks as a convolutional part as it is, and you put your new data, or you put your new fully connected part for a different problem. I want to show you an example of how I use it. That is a website called Kaggle, and so Kaggle like this, and this is a machine learning competition website. So since at ESOC I don't have that much opportunity to work with images, and I want something more challenging to keep motivated learning that, I decided to participate in this competition. This is one for learning only. There are other competitions with money associated, but I was interested in the learning part. And this is about to detect if these plants are appearing in the jungle. So there are some species which are invasive, and they basically take the plants that they should be living there, no? And they overtake. And what they say has a damaging effect on the environment, economy, and even human health. So it looks serious. So this on the left are the shape, or how they look like the invasive, and this look the local species. So what I did was exactly what I told you, is I took this network that was already trained, I took out this part, and I use a different fully connected architecture so that I have two output, so it's invasive or not. So I got a good result. So the maximum was 1, and I got 0.99, 175, not bad. The researcher who was in charge of this activity contacted me. He said, well, you know, I was thinking to wait till the contest was finished, but I don't think anyone can do better. So for me it was good, but the contest continued, and this is what happened. So I was not the first, not the second, so I was actually the 60th. But if you realize, you see how the competition is, because once you're doing like a 99 out of 175, is this guy is 99.7, no? When I tell the stories to some of my friends, yeah, but you're 60 out of 62, sure, no? So, but I want to put to tell you there is more people. And this is for convolutional neural network, another typical architecture, or not typical because it's very new, but very famous these days, is recurrent neural networks. So there are networks that have a memory, and they are able to remember and forget as data come and goes. This is a bit more tricky to have a mathematical intuition on this, and I realize it will take quite a long time to explain. So what I decided that instead of going to the mathematical part, I give you an intuition of what they can do, and maybe this we do for the next release of this machine learning series. So this is how it works. So you have input, you have output, and they have a hidden state. And when you use it, in reality what's happened is that this state is unrolled, and you can use it in different ways. Let me show you some examples on how you can use it. So if you use like one-to-one, this is the normal neural network. It's just for completeness. But you can have one-to-many, many-to-one, many-to-many, and many-to-many in a different way. Let me show you an example for each of them and where they're useful. For instance, one-to-many, I like this application. Image captioning. So your input could be a picture, and the output is the caption. So this caption has been written by a neural network. So you will collect many pictures, you will have somebody labeling them, possibly you can take it from the newspapers also, you need to do for the task, so it's already there. And what happens is that you will give a new picture and you will get a sensible description. Example of many-to-one. This is I took some reviews from Amazon, and the many part will be you have many words. So you can put your words there, and the one is that I want to predict the rating. So I want to know how many stars for this text. How is that useful? Because I can go to Amazon or whatever and get this data. So I have the text, I have the number of reviews, I can train my model, and then if I'm a company that is selling a product or a service, and I see people talking on Twitter or Facebook or whatever, or a forum, if I want to know from their comments if they're talking in a positive way, a negative way, equivalent number of stars of this comment, I can put their text and understand automatically without spending time how popular it is. Example of many-to-many. I'm sure all of you know this one. So you will put as an input your words in one language, and you will get the deep network to produce another set of words, another sequence of words in a different language. So this part is called the encoder. It will encode your sentence in a hidden state that summarizes what you want to do, or what you're saying in one language, and it will produce the decoded part in a different language. You can, by the way, you can also use this by chatbots. So you can have question, answer, or you can have a conversation. I mean, it's still not perfect, but some people are using for very close domain, like IT support, and it has some sensitive output, I would say. Many-to-many in a different way. Who has heard this news? An AI is writing the new Game of Thrones. So basically, how you do it is that you put all these books that are written till now, and you can do a character by character or word by word, as you like, and say, if I give you this word, give me the next. If I give you this word and the next and the previous to the next, and so give me what can happen in the future. So you leave it running, and it produces however many books you want. So this is a bit for the intuition. This is a small summary of we discussed today. And for me, the interesting part, I mean, it's not fancy, but the vanishing gradient, how the problem was solved, is that what allowed us to have deep learning architecture. But of course, the application are fantastic. all these slides and videos and other programming exercises are available or will be available in the Data Analytics ESA Connect community. For hands-on exercise, we're going to do now after this session, understanding which character is written. And that's all from my side. I will say that before starting the exercise, we have some time for questions. Before that, let me remember that the next session we will cover unsupervised learning, and in the original program was in H1, but has been moved to the press room on April 11, same time. So, any question from your side?